Hello dear students, in this video we will have a recap of the various concepts that we have studied in inferential statistics. First we will see the difference between population and sample. A population is a group of all distinct individuals or objects that a person wants to draw conclusions about. So the population consists of the group of all those individuals or objects which a researcher wants to study. The number of individuals or objects in this population, it is called population size. It is not always easy to collect information from each and every individual or each and every object in the population. So what a person does, or in general in statistics, the researcher will use a sample from the population to study about this population. So in statistics we commonly use a sample, that is a small subset of a larger set of data for making inferences about this large set. Here the largest set is the population out of which a sample is drawn, and the number of individuals or objects in the sample, it is called sample size. So the process of drawing a small subset which is called the sample from the population, it is called sampling. This process is called sampling. Sampling is a technique of selecting small group of population for estimating the characteristics without having to investigate every individual. So if we want to go in search of each and every person in the population, then it is difficult for the researcher. So what the researcher can do is, the researcher can draw a small subset from this entire population, then which is called the sample, and then the sample individuals can be studied and conclusions can be drawn about the population based on this sample. Now these are the steps involved in sampling. The first step is identify and define the target. So this is based on the study which the researcher is going to conduct, and then the next step is selecting the sampling frame. Sampling frame is nothing but it is the list of all individuals or objects that is available in the population, that is called the sampling frame. Then we have the sampling methods, and then we have to determine the sample size, and finally we can collect the required data. The broad category of sampling methods consists of probability sampling and non-probability sampling. A probability sampling is a sampling in which each and every object or individual in the population is having an equal chance of being selected in the sample. Such a sampling is called probability sampling. Whereas in non-probability sampling, not every individual or object in the sample will have equal chance to be selected in the sample. Here in probability sampling, there is an element of randomization, whereas in non-probability sampling, there is no randomization involved. Under this probability sampling, we have simple random sampling, stratified sampling, systematic sampling, and cluster sampling. In simple random sampling, every individual in the population has equal chance to be selected in the sample, and here they are randomly selected. Such a sample is called simple random sample. The next type of probability sampling is stratified random sampling. In this stratified random sampling, the entire population is divided into strata, and the sample is selected from each strata, and these strata are divided based on age, gender, income, and so on. And next we have the systematic random sampling. In this systematic random sampling, here every nth individual or nth object in the population are being selected in the sample. Say for example, in a class of 100, if we want to select 20 students, then every fifth student is included in the sample, which is based on the roll number. So such a sampling is called systematic random sampling. And the next type of sampling is cluster sampling. Here again the population is divided into various clusters which is based on regions or states and so on, and sample is selected from each cluster so that there is equal representation of population. Such a sampling is called cluster sampling. Then moving on to non-probability sampling. The first one is convenience sampling. Here the researcher selects those objects or individuals who are convenient to the researcher into the sample. Such a sampling is called convenience sampling. And then we have the next sampling which is quota sampling. It is similar to the quota system which is used in the education system. Next we have what is called purposive sampling. Here in this purposive sampling or judgmental sampling, the judges or some persons will decide who should be included in the sample. That is purposive sampling. And finally, we have snowball sampling. In this snowball sampling, it is usually used for sensitive issues. If a researcher wants to study about the child labor, then snowball sampling can be used. In this sampling, the researcher will first approach one person, and then that one person will direct to still two other persons, and those two persons will direct to still some more persons, who all will be included in the sample. So it is like a snowball. Such a sampling is called snowball sampling. And then we have representative and unrepresentative as a sample. A sample which accurately represents, reflects or matches with the features of population is called representative sample, and it must be an unbiased reflection of the population. So such a sample is called representative sample. Next we have unrepresentative sample. Here when the statistic does not represent the population parameter, then it is called unrepresentative sample. Next we have biased and unbiased sampling. In unbiased sampling, every individual or elements in the population have an equal chance of being selected in the sample. That is unbiased sampling. And then we have the biased sampling. If the sampling process systematically favors certain outcomes over others, then it is said to be a biased sampling. So these are different ways in which sampling methods can be classified. Now we have what is called parameter and statistic. Parameter, it is a characteristic of a population, and statistic is a characteristic of a sample. And if we see parameter, it is a numeric value which is taken from the entire population, whereas statistic is a numerical value which is taken from a sample and it is calculated from the sample observations alone. Say for example, population mean, it is taken from the entire population, whereas here sample mean, it is taken from only the sample observations. And then the next difference between parameter and statistic is the value of a parameter is computed from all population observations, whereas the value of the statistic is computed only from a portion of population which is sample. And then coming to the notations. The population parameter, they are denoted by Greek alphabets. The mean is denoted by mu, standard deviation by sigma, and variance by sigma square. The statistic, it is usually denoted using English alphabets. The mean is denoted by x, standard deviation by s, and variance by s square. So this is an example. If you want to calculate the average income of people of some specific region, then we will take the mean income and standard deviation of these incomes as parameters. On the other hand, in that specific region, if we consider 1000 residents from South Delhi alone, then it is a sample. So if we collect the mean and standard deviation of income of 1000 residents from South Delhi, then it is called a statistic. Here the mean income and the standard deviation of these incomes are parameter, and here the mean income and the standard deviation of income are sample statistic values. Now moving on to sampling errors. The difference between a population parameter and a sample statistic is known as the sampling error. So it is the difference, so it can either be positive or negative. And one important thing is this sampling error decreases as the sample size increases. So sampling error is equal to x bar minus mu, where X bar is the sample mean and mu is the population mean. Population mean is calculated as summation xi upon population size and sample mean is calculated as summation xi upon sample size. Now there are various reasons for sampling errors. The first one may be the population parameter is estimated differently by different samples, or it can be because of faulty selection of sample, or it can be due to small size of sample. And now one more reason may be the sample results have potential variability. Now moving on to statistical significance. Here the duty of the researcher is to draw a sample wisely in such a way that the sample is a true representation of the population. Now how we can check whether the sample is a true representation of the population? This is usually done using statistical significance. Statistical significance, it is a measure of reliability of the findings which is made on the population based on the sample. It means how confident the researcher is about the findings and whether the sample was framed wisely. Now moving on to sampling distribution. We have already studied about probability distribution. Probability distribution, it is a distribution of a random variable x. Similarly, sampling distribution of a statistic, it is a distribution of all possible values which is taken by the statistic when all possible samples of fixed size n are taken from the population. So it is similar to a distribution. Here sampling distribution is the distribution of a sample statistic. Say for example, we can have sampling distribution of mean. Now next we have what is called standard error of mean. Now this standard error of mean, sigma m, it measures how much dispersion there is likely to be in a sample mean compared to the population mean. That is, it measures the standard deviation of sampling distribution about the mean. So this standard error of mean, it is calculated as sigma m is equal to sigma by root n, where n is the sample size and sigma is the population standard deviation. And now what is the use of this standard error of mean? If there is a small standard error of mean, it means it gives us confidence that our estimation of the population mean is relatively accurate. On the other hand, if we have a large standard error of mean, it means we have small number of observations and they vary a lot and the population estimation is likely to be inaccurate. So if this value is less, it means our estimation is good. If this value is large, it means we have only small number of observations and those observations also vary a lot and the estimation which we make on the population based on the sample, it is not very accurate. Now we have a question based on the standard error of mean. A sampling distribution of the sample means x bar is formed from a population with mean weight mu is equal to 80 kg and standard deviation sigma equal to 14 kg. What is the expected value and standard deviation of x bar if sample size is 49? So here we have a sampling distribution of the sample means which is formed from the population with mean weight mu as 80 kg and standard deviation sigma is 14 kg. We need to find the expected value of x bar and standard deviation of x bar. They have given the sample size as 49. Similar question was given in the sample paper for 2 marks. So let us solve this. First let us write what is given. Given mu equal to 80 kg, sigma equal to 14 kg and sample size n is 49. Here we are asked to find expected value of x bar. Now we know that the expected value of x bar, that is the expectation of x bar, it is equal to mu. So from this we have expected value of x bar equal to 80 kg. Then we are asked to find the standard deviation of x bar. Standard deviation of x bar is nothing but it is the standard error of mean, which is sigma m. Sigma m is nothing but it is sigma by root n. So here sigma is 14 and n is 49. So 14 by root 49 is 14 by 7, which is 2. So the standard error of x bar, it is equal to 2. So finding the value of expected value of x bar, this carries 1 mark, and standard deviation of x bar, that is the standard error of x bar, this step carries 1 mark. Now moving on to central limit theorem. This is a very important theorem in statistics. Central limit theorem, it implies that the distribution of a sample leads to become a normal distribution as the sample size becomes larger, considering that all the sizes of sample are identical, whatever be the shape of the population distribution. So according to this theorem, the sampling distribution leads to become a normal distribution as the sample size becomes larger. Now, if we remember the normal distribution curve, it is a bell-shaped curve. So it is important that we have to increase the size of the sample so that the sampling distribution becomes a normal distribution. A sample size of 30 or more is considered to be sufficient to hold central limit theorem, and as the sample size becomes large, the prediction of characteristics of population becomes more accurate. So this is the implication of central limit theorem. And now we have confidence interval. We use confidence interval to express precision and uncertainty of a sampling process. So we cannot always say we are 100% sure that the estimation that we make about a population based on the sample is true. So we use what is called confidence interval. So there are three components in a confidence interval. The one is confidence level, then we have statistic, and then we have the margin of error. The confidence level, it explains the uncertainty of a sampling method. Say for example, we can say we are 95% sure that the population mean is some real number. Say for example, 95% confidence level. Then we have the statistic. Statistic, it is calculated from the sample which is used to estimate the population parameter. This statistic we will study while we are discussing about hypothesis testing. And then we have margin of error. It describes the accuracy of a sampling method. The margin of error, it shows a range of values within which the population parameter can lie. That is margin of error. Next we have hypothesis. In order to make decisions about the population, we have to make some assumptions about the population. Such assumptions, which may or may not be true, they are known as hypotheses. They are tentative declarative statement about relationship between two or more variables. So under hypothesis, we have two types. One is the null hypothesis H0, and the next one is the alternate hypothesis H1. The null hypothesis, it states that there is no difference between a parameter and a specific value. So usually null hypothesis, it is given by the population parameter mu, it is equal to some value mu naught, or it states that there is no difference between two parameters. Or if we have two different population, it states that the two population are same, that is mu1 equal to mu2. It is a statement of no relationship. Or it states that the two groups that we are studying are same. Next we have the alternative hypothesis. It is just the opposite of null hypothesis. It states that there is existence of difference between a parameter and a specific value. It states that mu not equal to mu naught, or it states that there is difference between two parameters, mu1 not equal to mu2, or it says that the two groups that we are studying are different. So this is with respect to null hypothesis and the alternate hypothesis or alternative hypothesis. Next we have the degrees of freedom. Degrees of freedom, it is nothing but it is the number of independent pieces of information on which an approximation is based. This is known as degrees of freedom. Now let us take an example of degrees of freedom. Say we want to find 4 natural numbers whose sum is 10. Say if we take the first three natural numbers as 1, 2 and 3, then the fourth natural number which we have to take, it is only 4. So only then all these will add up to 10. So here we are free to choose the first three natural numbers, whereas the fourth one, it is based on the result. So here the degrees of freedom is 4 minus 1, which is 3. So this is with respect to degrees of freedom. And now we have level of significance. In hypothesis testing, the level of significance is the probability of making a wrong decision when the null hypothesis is true. Say for example, if we have t-test, then we have to test the hypothesis. Say if we have h0 as mu equal to some number mu naught and h1 as mu not equal to mu naught. Now sometimes we may get the result in the t-test as the null hypothesis is rejected. But on the other hand, the null hypothesis may be true. So that probability of making a wrong decision when the null hypothesis is true, that is rejecting h0 when it is true, it is called level of significance and it is denoted by alpha. And now we have hypothesis testing using the t-test. Under t-test we have two types. One is the one sample t-test and the other one is the two independent sample t-test. This one sample t-test, it is also called a small sample test. We can use this t-test for sample size of less than or equal to 30. And in this one sample t-test, the degrees of freedom is given by n minus 1, where n is the sample size. And next we have two independent sample t-test. Under two independent sample t-test, we have two cases. The first case is when the population variances are assumed to be equal, and the second case is the population variances are assumed to be unequal. So we will see each of these type now. Now first we will see what is one sample t-test. If you see this t-test, it is a statistical test for the mean of a population and it is used when the population is normally or approximately normally distributed with an unknown variance. So the t-test, it is used to test the statistical significance of the mean of a population when the variance of the population is not known. So if we take let x1, x2 up to etc. xn be a random sample of size n from a normal population with mean mu and variance sigma square, then the student t statistic, it is given by t is equal to x bar minus mu upon capital S by root n. So here n is the sample size, x bar is the sample mean. X bar is the sample mean and we have this, the value of this S square, it is given by 1 by n minus 1 summation xi minus x bar the whole square. So if the sum of squares of deviation from the mean is given or if the sample observation is given, then we can use t is equal to x bar minus mu upon capital S by root n, where S square is given by 1 by n minus 1 summation xi minus x bar. On the other hand, if the sample standard deviation is given, if this small s, so the sample variance is given by 1 by n summation xi minus x bar the whole square. If this is given, then we have to use the t statistic as x bar minus mu upon s by root of n minus 1. So if the sample variance or if the sample standard deviation is given, then we can use this formula. On the other hand, if the sample observations xi are given, we can use this formula to find capital S, or if the sum of squares of deviations from the mean If it is given, then again we can use this capital S. Now there has been a big confusion with respect to this capital S and this small s. We have studied that the expected value of x bar, it is equal to the population mean mu. That is, expectation of x bar is equal to mu. Now this S square, it is an unbiased estimator of the population variance. Now we are using this one sample t-test when the population variance is unknown. That is, we do not know the value of sigma square. When we do not know the value of sigma square, then we have to use the expected value from the sample. So if we take this S square, the expected value of this capital S square, it is equal to sigma square. So this is basically called unbiased estimator of population variance. On the other hand, expectation of small s square, it is not equal to sigma square. So we cannot use small s upon root n in this t statistic. It is because of this reason. So we have to use t is equal to x bar minus mu upon s by root n if capital S is given. Otherwise, if small s, that is the sample standard deviation, is given, then we can use t is equal to x bar minus mu upon s by root of n minus 1. So this is with respect to the t statistic that we have to use for t test, and it is given by students t statistic. And now moving on to the application of t test. So the use of t test is to determine whether the null hypothesis should be rejected or not. So as far as the syllabus for the academic year 2021-22 is concerned, we are having non-directional hypothesis. So the hypothesis is non-directional. It means if we take h naught as mu equal to mu naught, then the alternate hypothesis h1, it is mu not equal to mu naught. So this, in a non-directional hypothesis, we have to use two-tail t-test. Now here is the procedure for testing the hypothesis using t-test. The first one is we have to state the hypothesis. We have to state what is the null hypothesis h naught, say mu equal to mu naught, and the alternative hypothesis h1, say mu not equal to mu naught. And then the second step is we have to define the statistic. That is, we have to find t. And then we have to find the value of t and then the tabulated value of t with n minus 1 degrees of freedom and alpha level of significance. So after finding the value of the t statistic, we have to find the critical value or the table value of t with n minus 1 degrees of freedom. For this one sample t test, the number of degrees of freedom is given by n minus 1 and the level of significance is given by alpha. Then the next step is we have to make the decision to accept or reject h naught. And the last step is we have to summarize the results. Now if we see the t distribution table and the critical t values, they have given area in one tail for various levels of significance and area in two tails for various levels of significance, and we have the degrees of freedom here. Now if we take a left tail test or a right tail test, say for example, if for a left tail test alpha is 0.025 and the degrees of freedom is, let us say, 9. So for a left tail test and for degrees of freedom 9, we have to see area in one tail, and here for 0.025 and 9 degrees of freedom, the critical t value is 2.262. So this is the critical value. It means here we have for alpha equal to 0.025. So here we have negative 2.262. Similarly, if we have a right tail test for alpha equal to 0.025 and degrees of freedom equal to 9, then the critical t value is positive 2.262. This is positive 2.262. If we take hypothesis testing of this type, where the alternate hypothesis is mu not equal to mu naught, then this is a two-tailed test. So here we have to see area in two tails. Here if we see the area in one tail for 0.025 and area in two tail for 0.05 and for 9 degrees of freedom, the critical t value is the same. It is 2.262. Here for a two-tailed test, alpha equal to 0.05, here we have alpha by 2. Here we have 0.025 and here we have the remaining area 0.025. So here the critical value here it is plus 2.262 and the critical t value here it is negative 2.262. So if the calculated value of t, if it falls in this region from this part to this part, if it falls in this region, then we have to accept H naught. If it falls here, we have to accept H naught. On the other hand, if it falls in this region, that is if the critical t value is more than 2.262, it means the value falls in this region. This region is called the region of rejection. Similarly, if the value of t is less than minus 2.262, then again it falls in this region. This region is the region of rejection. So if the value of t falls in these two regions, then we have to reject H naught. So this is what we have to do as far as the t-test is concerned. So that is the fourth step. We have to make the decision to accept or reject H naught, which is based on the value, the tabulated value of t and the value of the t-test statistic. And finally, we have to summarize the result. Now here summarizing the result is, we have to write the result based on what is asked in the question. So these are the steps that we have to go about when we perform t-test. Now let us see an example for one sample t-test. Similar questions can be expected for 3 marks. Similar question was asked in the sample paper for 3 marks. I have taken this question from Oswald's sample paper. A machine which produces mica insulating washers are used in the electric devices is said to turn out washers having a thickness of 10 mils. Here 1 mil is equal to 0.001 inch. A sample of 10 washers has an average thickness of 9.5 mils with a standard deviation of 0.60 mil. Find out t. Now this question I have added extra. Interpret the result at 5% level of significance given t 0.025 equal to 2.262 at nu equal to 9. Here nu is nothing but it is the degrees of freedom. So at 9 degrees of freedom, the critical t value, here the area in one tail is given because we are asked to interpret the result at 5% level of significance. So here it is given a machine produces washers having thickness of 10 mils. A sample of 10 washers has an average thickness of 9.52 mils and a standard deviation of 0.6 mils. We have to find out t and we have to see whether this average it is significant or not. So first let us write. Define null hypothesis H naught and alternate hypothesis H1 as follows. So we have H naught as mu equal to, here the machine has to produce a thickness of 10 mils. So mu equal to 10 The alternate hypothesis H1 is mu not equal to 10. Here, since we are having alternate hypothesis H1 as mu not equal to 10, it is a non-directional hypothesis, so we have to use a two-tailed test. Thus, a two-tailed test is applied under H0. So we have T is equal to x bar minus mu upon small s by root n minus 1. So it is x bar minus mu upon s into root of n minus 1. So here we have x bar is, here the sample mean, it is 9.52. Then the sample standard deviation is 0.6 and n is 10. So we have T as 9.52 minus 10 upon 0.6 into root of 10 minus 1, which is 9. So we get T as minus 0.48 upon 0.6 into 3. So this is negative 2.4. So here we can see that T is negative 2.4. So it does not lie in the interval minus 2.262 to plus 2.262. So if we take the graph, so here it is alpha by 2 means 0.025 and here alpha by 2 means 0.025. Here it is negative 2.262 and this is positive 2.262. This is the region of rejection. So we have negative 2.4. This negative 2.4 lies in this region. It is less than negative 2.262. So we have to reject H0. So the result is we have to reject H0. Since T equal to minus 2.4 does not lie in the interval negative T 0.025 to T 0.025, that is negative 2.262 to 2.262 for 10 minus 1 equal to 9 degrees of freedom. We reject H0. So since this value does not lie in this interval, we reject H0. Therefore, here we can conclude that if H0 is accepted, then the machine is working properly and it is producing washers of thickness 10 mils. Here, since H0 is rejected, it means the machine is not working properly. Therefore, the machine is not working properly. So here writing the null hypothesis and alternate hypothesis carries 1 mark, finding the value of T carries 1 mark, and the remaining steps and the result carries 1 mark. Now let us see a case to find the value of T when the sample data is given. Say for example, when the sample data is given, say for example xi is given as 1, 4, 7, 3. Here summation xi is 15. So if we want to calculate S when the sample data is given, we can calculate S square as 1 by n minus 1 summation xi minus x bar the whole square. So here say for example for this data we got summation xi as 15, x bar will be summation xi by n. So here we have 4 observations, so n is 4, it is 15 by 4, which is 3.75. So if we want to calculate S square using this formula, xi minus x bar summation xi minus x bar the whole square upon n minus 1, then we have to do xi minus 3.75. So here we will have fraction values. Then we will have xi minus 3.75 the whole square. Again we will have to do huge calculations. So what we can do is we can use assumed mean and then we can find the value of s square. So this we can find it as 1 by n minus 1 into summation di square minus 1 by n summation di the whole square. Here di is xi minus a. Di equal to xi minus a, where a is the assumed mean. So here say for example we can take the assumed mean as 5. So we can find di as xi minus 5. Di as xi minus 5. So here we will have minus 4 minus 1, 7 minus 5 is 2, 3 minus 5 is minus 2. Here we can find summation di easily and we can also find di square. Di square will be 16, 1, 4, 4 and summation di square also can be found easily. We can substitute those values here and we can find the value of s square. So we can make use of this formula for s square when the sample data is given. Now let us see an example where we have to use one sample t-test when the sample data is given. Find the student's t for the following variable values in a sample of 8. Minus 4, minus 2, minus 2, 0, 2, 2, 3, 3, taking the mean of the universe to be 0. So this question was also taken from Oswald's sample paper and I have added one more question. Interpret the result at 5% level of significance. Given t 0.025 equal to 2.365 at nu equal to 7. So for 7 degrees of freedom, the critical t value, that is the area in one tail, is 2.365. So again let us take define null hypothesis H0 and alternate hypothesis H1 as follows. So we have H0 as, here they have taken mean of the universe as 0. So H0 is mu equal to 0 and H1 is mu not equal to 0. Thus we can see that a two-tailed t-test is applied under H0. So we have t equal to x bar minus mu upon s by root n, where s square is given by 1 by n minus 1 summation xi minus x bar, the whole square. Again here, since it will be difficult to find xi minus x bar the whole square, the calculation may become tedious. So let us take this is equal to 1 by n minus 1 into summation di square minus 1 by n summation di the whole square, where di is xi minus the assumed mean. So here we have xi. Let us take the assumed mean as 1 xi minus 1, which is di and then di square. So for xi the values are minus 4, minus 2, minus 2, 0, 2, 2, 3, 3. So here minus 4 minus 1 is minus 5, minus 2 minus 1 minus 3, minus 3, minus 1, 1, 1, 2, 2. So here summation xi, it is equal to 2 and here summation di, it is equal to it is negative 6. And now let us find di square. Di square, it is 25, 9, 9, 1, 1, 1, 4, 4. So this when we add, we get summation di square as equal to 54. So summation di square is 54. So now let us find s square. S square is 1 by, here the number of observations is 8. 8 minus 1 into summation di square is 54 minus 1 by n. N is 8 into summation di the whole square. So this is 1 by 7 into 54 minus 36 by 8. It is 4.5. So this is 49.5 by 7, or it is 7.07. So we have got s square as 7.07. Now we have to substitute s here. Then x bar is equal to summation xi by n. It is 2 by 8. So this is 0.25. So x bar is 0.25. Now here we got s square as 7.07. We need to find s. So s square is 7.07. Now let us find s. So let us find the square root, 7.07. We have to take integral value separately and decimal value separately. So here we have 2 into 2 is 4. Then if we subtract 7 minus 4 is 3. Then bring the next to 2 digits. Let us keep a point here since there is a decimal point. Now we have plus 2 here. 2 plus 2 is 4. And now here if we see, we can try 46 into 6. So we can put 6 here, 6 here. We get 276. This when we subtract, we get the remainder as 31. So now again if we want another one more decimal value, let us add still 2 more zeros. Adding zeros after the decimal point does not change the value. So let us bring these 2 zeros next. Now after this we have to add this 6 to this divisor. So 46 plus 6, it is 52. So let us try 5. We get 2625. This when we subtract, we get 475. So let us stop with 2 decimal values. This implies s is equal to root of 7.07. It is 2.65. And then now we can find, and we already got x bar as 0.25. So t is equal to x bar minus mu upon s by root 10. So x bar is 0.25, mu is 0 upon s is 2.65 upon root n is root 8. So it is 0.25 upon 2.65 into root 8 is 2 root 2. Since root 2 value we know it is 1.414. So let us substitute that and we can simplify this. When we simplify this, we get the value of t as 0.267. So they have given t 0.025 equal to 2.365 at nu equal to 7. So the calculated value of t, it lies in the interval. So they have given t 0.025 as 2.365 for nu equal to 7. Since t equal to 0.267, lies in the interval minus t 0.025 to t 0.025, that is minus 2.365 to 2.365 for 8 minus 1 equal to 7 degrees of freedom. We accept H naught. So here they have given, we have to take the mean of the universe as 0 since we accept H naught. Therefore, mean of the universe is equal to 0. That is, the population mean is equal to 0 for this sample data. Now we have the next type of t-test, which is t-test for two independent groups. Now this test, it compares two groups and helps us to see whether a statistical significance exists between the two means. So those two groups can be considered as the experimental group and the control group. Here the experimental group is the group which receives treatment and the control group is the group which does not receive any treatment. The treatment can be any study. Say for example, if a person wants to test the effect of yoga on individuals, so the researcher can divide the entire group into experimental group and control group, and in one group the respondents will be asked to perform yoga, and the effectiveness of yoga will be tested by comparing the experimental group and the control group. So this is basically t-test for two independent groups. Here the two sample t-test, it compares the means of two groups. Under this two sample t-test, we have two forms of test statistic. The case one is when the variances are assumed to be equal. So when we have two independent samples which are drawn from population with identical population variance, that is the variance of the two groups, if they are equal, then the t-test, it is given by t equal to x1 bar minus x2 bar upon sp into root of n1 n2 upon n1 plus n2. So here x1 bar is the sample mean of the first sample and x2 bar is the mean of the second sample. N1 is the first group's sample size and N2 is the second group's sample size. Here SP is called the pooled standard deviation, where SP square, which is the pooled variance, it is given by N1 S1 square plus N2 S2 square upon N1 plus N2 minus 2. So this is called the pooled variance, where S1 is the standard deviation of the first sample, S2 is the standard deviation of the second sample, and SP is called the pooled standard deviation, or it is the combined estimate of the overall standard deviation. So this is the first case. Now in this t-test for two independent groups, the degrees of freedom, it is given by N1 plus N2 minus 2. In one sample t-test, we used to have N minus 1 degrees of freedom. Here for one sample we have, for the first sample we have N1 minus 1. Then for the second sample we have N2 minus 1. So the degrees of freedom is given by N1 minus 1 plus N2 minus 1. So it is N1 plus N2 minus 2. So the degrees of freedom for the t-test for two independent groups, it is given by N1 plus N2 minus 2. Now let us see an example for this two sample t-test. Samples of two types of electric bulbs were tested for length of life and the following data were obtained. Number of bulbs in the sample. For type 1 we have 8 bulbs and type 2 7 bulbs. Mean in hours. Type 1 the mean is 1134 hours and for type 2 it is 1024 hours. And then the standard deviation for type 1 is 35 hours and for type 2 it is 40 hours. Here we are asked, is the difference in the sample means significant? Given t 0.025 equal to 2.16 for nu equal to 13. So here we have to test whether the sample means are significant. So let us define null hypothesis H0 and alternate hypothesis H1 as follows. H0 is mu1 equal to mu2, that is, there is no significant difference between the means, and the alternate hypothesis is mu1 not equal to mu2. Since we have mu1 not equal to mu2, we have a two-tailed t-test which is applied under H0. Therefore, we have t is equal to x1 bar minus x2 bar upon sp into root of n1 n2 upon n1 plus n2. So here x1 bar, x2 bar, n1, n2, all these are given in the question itself. Sp we have to find, where Sp square is equal to n1 s1 square plus n2 s2 square upon n1 plus n2 minus 2, or it is n1 is 8, s1 is 35, so 8 into 35 square, plus n2 is 7 and s2 is 40, 7 into 40 square upon 8 plus 7 minus 2. So this, when we simplify, we get 9800 plus 11200 upon 13. So it is 21,000 by 13, or it is 1615.38. So we got Sp square as 1615.38. We need Sp. So let us find root of this. Sp is equal to root of 1615.38. So 1615.38, if you want to find the root up to 2 decimal places, we need to have 4 digits after the decimal point. So divide the integral part and the decimal part as pair of digits. So first we have 16, 4 into 4 is 16. So we get 0, bring the next pair of digit. Now add this 4, we get 8. Here even 81 into 1 will not be more than 15. So here we have 80. So here we have to bring the next pair of digit. Since there is a decimal point here, we can keep a decimal point here as well. And then we have, next we have 80. It is 801. 737. Now let us bring the next pair of digits, 0, 0. If we add this one here, we get 802. If we use 9, then 8029 into 9, it is we get 72,261. So here we get the remainder as 1439. So we get root of 1615.38 as 40.19. So this is equal to 40.19. So we got Sp as 40.19. Now we can find T. T is x1 bar. x1 bar is 1134 minus x2 bar is 1024 upon Sp is 40.19 into root of n1 n2. 8 into 7 upon 8 plus 7. So this, when we simplify, we get it as 110 upon 40.19 into root of 56 by 15. So it is 3.73. Now let us find the square root of 3.73. Again, we have to take the integral part separately and the decimal part separately. If we want to find the square root up to 2 decimal places, let us add 2 more zeros. Now if we see 3, we have to take 1 into 1. The remainder is 2. Now if we add 1 plus 1, we get 2. Let us bring the next pair of digits and place a decimal point. Next we have 2. If we take 29 into 9, we get 261. So the remainder is 12. Now let us bring the next pair of digits. Here we have to add 9. So our next divisor is 38. So 383 into 3. If we see, we get 1149. Here the remainder is 51. So square root of 3.73 up to 2 decimal places, it is 1.93. So it is 110 upon 40.19 into 1.93. So this, when we simplify, we get it as 5.28. Now we can see that this 5.28, it is more than 2.16 for nu equal to 13. So we have to reject H0. Since t equal to 5.28 does not lie in the interval minus t 0.025 to t 0.025. That is negative 2.16 to 2.16 for n1 plus n2 minus 2. That is 8 plus 7 minus 2 equal to 13 degrees of freedom. Therefore, we reject H0. We reject H0. It means the difference in the means are significant. Therefore, difference in means are significant. So this is with respect to two sample t-test when the population variances are assumed to be equal. Now next we have the last method to find the t-test statistic when the variances are assumed to be unequal. When the variances are not equal. Here the t-test is given by t-test statistic is calculated using this relation x1 bar minus x2 bar upon root of s1 square by n1 plus s2 square by n2, where x1 bar, x2 bar are sample means and s1 square and s2 square are sample variance. n1 and n2 are sample sizes. Now when the variances are assumed to be equal, we had the degrees of freedom as n1 plus n2 minus 2. Here when the variances are assumed to be unequal, the degrees of freedom is calculated using s1 square by n1 plus s2 square by n2 the whole square, the whole thing divided by 1 by n1 minus 1, s1 square by n1 the whole square plus 1 by n2 minus 1, s2 square by n2 the whole square. So this is how the degrees of freedom is calculated when the variance are assumed to be unequal. I hope this video was useful for you. Thank you for watching.